A modern baseball cap functions as a specialized biomechanical tool. It is engineered exclusively to grip the flat, vertical forehead of a Homo sapiens and wraps snugly around a perfectly round, globular skull. If you placed this exact hat on our extinct hominin cousins, it would fail completely. Their long, backward-sloping foreheads would offer no grip, causing the cap to slide right off. And because they completely lacked a protruding bony chin, any modern helmet strap would simply slip down their throats. Complex intelligence is not restricted to our specific skeletal shape. Because these ancient humans possessed radically different anatomies, solving the basic problems of survival required them to engineer entirely different physical tools. Imagine a divergence roughly 300,000 years ago. The ancestral population of anatomically modern humans goes extinct. Our hyper-globalized industrial world is never built. The Earth is instead inherited by a highly diverse triumvirate of archaic humans. The heavy-boned Neanderthals take the glacial west. The altitude-adapted Denisovans claim the eastern steppes, and the diminutive Homo floresiensis master the tropical archipelagos of the south. This alternate timeline does not result in a stagnant, primitive wilderness. Left to their own devices, these three lineages converge on advanced civilizational states, engineering tools and societies perfectly suited for the planet's most extreme environments. To survive the freezing, heavily forested environments of Ice Age Europe, Neanderthals relied on massive, barrel-chested frames. Maintaining this extreme muscle mass required up to 5,000 calories a day, turning them into highly specialized apex predators. The low-light environment of northern latitudes forced a brutal evolutionary trade-off. Neanderthals developed enormous eye sockets to maximize light capture, dedicating huge portions of their brain to visual processing. This left significantly less neural volume for the social brain, strictly capping their natural community size at around 120 individuals. Look at the skeletal profile on the bottom left. This rounded protrusion is the occipital bun, a dense bony cleat anchoring load-bearing neck muscles. Moving above, we see the occipital cowl, a heavy leather pocket hooking securely underneath that bun to counterbalance heavy front visors. Driven by their intense caloric needs and a hard biological limit on group size, Neanderthals bypassed the massive high-trust empires of our timeline. Instead, they forged an intensely individualistic network of heavily armored, highly territorial guild states. Moving east into the freezing, thin-air environments of the Asian steppes and the Tibetan Plateau, we find the domain of the Denisovans. This diagram shows their genetic advantage. Denisovans possessed a variant of the EPAS1 gene regulating oxygen transport. Where normal human blood dangerously overproduces clumping red cells at high altitudes, this gene suppressed that reaction, maintaining smooth, efficient blood flow under severe hypoxic stress. This photograph reveals their massive cranial architecture. The Denisovan skull was incredibly wide, featuring heavy brow ridges and a receding jaw devoid of a chin. Examine the center illustration of their headwear. To survive severe high-altitude UV radiation, they required wide-brimmed hats. Lacking chins to anchor straps, they invented an inward mastoid grip. This system clamped rigidly behind the mastoid process, the dense bone behind the ears, locking the hat. The EPAS1 gene allowed Denisovans to thrive, where oxygen levels would induce lethal cardiovascular trauma in other humans. By establishing permanent strongholds above 4,000 meters, they turned the planet's most extreme mountain ranges into unconquerable geographic fortresses, housing a highly collective society bound by a spiritual connection to the high-altitude landscape. Thousands of miles south, the sweltering, resource-starved archipelagos of Southeast Asia belong to Homo floresiensis. These hominins stood roughly 3.5 feet tall. They present a profound biological paradox. Their brains were roughly the size of a chimpanzee's, yet their prefrontal cortex, the neural region responsible for executive function and forward planning, was highly reorganized and structurally complex. However, this diagram reveals a fatal biomechanical flaw. Computer simulations show that if they attempted to chew tough vegetation or raw meat, the temporomandibular joint, the jaw hinge, would suffer dangerous tensile reactions, risking total dislocation. Look at the far right diagram. They engineered woven canopy hats suspended above the scalp to dissipate tropical heat. To secure these microcaps during a hunt, they relied on a soft submandibular web that distributed tension safely across the robust jawline and throat. Because they risked jaw dislocation from raw food, Homo floresiensis relied absolutely on fire and stone tools for every meal. This total dependence on external technology and coordinated group hunting drove them to master the sea, utilizing rudimentary navigation to bridge the gap between islands and establish a cooperative network across the Pacific archipelagos. Look at this landscape. Because these archaic humans hunted as up-close ambush predators and lived in smaller, strictly constrained populations, the mass extinctions of the Ice Age megafauna never occur. The Earth remains vastly wilder. We often assume that our specific, generalist body type is the inevitable pinnacle of evolutionary progress, but biology operates without an end goal. Where our timeline is defined by explosive, rapidly compounding technological disruption and planned obsolescence, these archaic societies prioritized intergenerational durability, perfect utility, and deep material resilience. The survival of these species reveals a world of specialized intelligence, from the high-altitude mountain capitals of the Denisovans to the waterproof maritime networks of the Floresians. It shows that civilization isn't tied to our specific globular skull. It is a functional outcome of anatomy adapting to the specific pressures of the environment.